back. So let's recap. Before the dinner break, I was trying to look into implementing this equation. I think we've gone as far as putting in the air velocity. This surface is also 4 square meters. And then I was going to do, what did we do? We did this part, this part. We were going to do these two parts. And they also depend on temperature. Now, let's close a few tabs here. I think we will look into this a bit later. Experiment. Okay, we actually okay with that. I don't think we need this. Done. So according to this, what we are trying to do here is this. I think I'm always going to assume that the water temperature will be fully game be tile based. I think tile based. You mean following a grid structure? It might. It most likely will. So, which means I have to come up with a certain like square size that I picked either 30 by 30 centimeters or 40 by 40. Yeah, I think it's going to be on a grid. Because that's how I got some of the assets designed by outsourcing company. So yeah, most likely it'll be like. But maybe we'll have some kind of space, like say, it's still going to occupy uh, 2 by 1 grids, but then the visual will not occupy that area fully. So we'll actually give you an illusion that there's some negative space around it. So that sort of thing. But will most likely be grid based. So I was thinking, what if the water temperature is 5 centimeters less than the air temperature? Because we'll be doing the air temperature. Like this. And sure, let's do temperature. Here is T, but we are bullshitting constants. We need a new name for temperature. Um, temperature. I don't want to put T because T is the time. T. I'm almost tempted to actually turn these into notation like this WLWH. Let's go with P for now. Temperature is 25. Can only be maybe it's 25. Fine. Pull you into constants. Where you are. Let's actually to there. What is the formula? So that when this is 25, this is 20, and humidity is going something like, let's call H as humidity 50%. When humidity is 50% is essentially, this can be maybe like this. between this and that. So here's your humidity percentage. Brilliant. Stick it in here. L was the lid, on or off. Rain is rain, that's fine. Moving forward. So, given air temperature and humidity, assuming this is always 5 degrees less, we need to get two numbers so that they should read like this. We have to do that based on this. How do we do that? Here's some kind of table, but where's the equation? Is this the equation? Humidity ratio by mass, that is not maximum saturation humidity. Humidity ratio by mass. The fact that there's some kind of chart like this, there's going to be equation. I can see that this being 20 and this is like 14 thousandth. This, sorry, 15 over 1000. This is almost another exponential equation. Here's the here's the 14.7. And this ties into a different equation. Is this over this minus this? What is this? Is that the same number that we saw here? No. Sixty-two 198. We actually got to that 62. Is that a constant? It is a constant. So here's the pressure. Is the atmospheric yeah, this is also, this is not exactly constant, but you measure the partial pressure, which is calculated based on this. This is the dynamic part. This is sort of somewhat dynamic, changes every day. You get this. Let's dig into this. Okay. I was right, but exponential. Here's our exponential function. Some constant plus some other constant times t. T being is what? The dry bulb temperature. Okay. What is dry bulb temperature of the these values are close enough that I think I will bullshit my way. Let's write a new equation. This is bullshit equation B. It is such that, so here's what I'm understanding. This is this exponential function, okay? That goes into, that is this value, magical. Then there's this thing that we measure. and Pascal, right? We actually we have this 101.2 that is going to be this value. We'll actually give this to the player. So we will have access to this. We just have to make sure that this value is coming in kind of okay from here. We'll kind of do a simulation of this. We just have to plug this in, and then we get this number. We get this number, we are in a happy place. This 20 is already taken into account here and here. And then this will actually give us the correct result for 20. Here 198. I think that is actually, yeah, that is the constant. Sorry, just have to figure this one out. Okay. I need to create some kind of equation that gives similar results here. So which one of these is the one we want? So we know that at 20 degrees Celsius, we need to get something over 2000. Here's 20. Scale seems a bit off, but this is the right graph. Because here, oh, this is Fahrenheit anyway. 20, we are getting 310, close enough. So this equation, the way they put it, something like, let's plug this in, bullshit equation. Is this over like E over e to the power of 8.2, or I think so. This is not part of this, right? E over, can actually do that. This, no, not that. See, this has to be first taken into the power over e to the power of 8.2. And what is t? Is the t that we need to take into account. So wrong here, this is correct. E in this case is different color. Let's pick it. This graphic has to look like right now it doesn't. Dry bulb temperature. I guess I'm assuming that 20 degrees is gonna be plugged here. PWS, PW is going to give is then gonna be, yeah, okay, makes, it's the Kelvin, Fahrenheit, whatever. First conversion from C to Kelvin. So yeah, they are plugging in the temperature. So that is actually our temperature. Then our temperature is in T. T is the temperature. By this part, and this is P. We are going to be P. This is giving us a horrible number. Is even correct. Yeah, I kind of want to punch this number. 208 times 005. Okay, that's the, then that's essentially this. Why could this? Okay, there's something wrong here. But over t, right? Okay, this is over t, not times t. Over 208. This is going to be minus plus 169. We are in this zone. We are done. Plus 45. Okay. E to the power of this. It's an enormous number. Okay, I know that. I don't need to do that. This is going to be the same number. That is not going to be possible to calculate basically. Well, it might be. It's really high. So 270 something here. Go scientific. 270 something. Sorry. Filled everything there. This looks different. It's as if it got an update. What am I looking for? I'm looking for E is 270. Yeah, it's going to be a huge number. However, you are going to divide that number by 280 to power 8.2. That's a huge number too. You are going to take this number. Let's put this in memory. Okay, let's clean the calculator. Let's call this from memory. E the power of over memory. Okay, that gives you some high number, which means that this part is not below the Euler number. It's part of the decimal sub. Means this is actually part of this, not that. The whole thing. How do you do? So this, cut this, do the power. That is what we want. Thank you. You need something before the superscript symbol. At times like this, I think it makes sense that we go to the good old Google Drive. Maybe I'll do a throwaway blank. Let's type in the numbers. So we have temperature, okay, 25. We have, what do we have? We have a bunch of constants, which is this. So I want to do this at least as, I'll pull this to the other screen so that I can actually do, say, this is like the, what? This is power part, okay? Power part will be such that we'll have 77.345 plus 0.0057 times temperature minus 7 to 35 over temperature. That's done. Okay, that is the power part. Now there is also the powerful temperature, very descriptive name, right? So that formula is that it's temperature, actually what, power, yeah, power, temperature 8.2. Okay, some insane number. Now question is, I'm just going to do this halfway here. So we have this temperature part described. Sorry, we have the temperature, and the power part that I'm highlighting here is this. So we need to combine these two and then the Euler number. So we get 2000 or something like that. Here's the formula. How do you get the constant E here? It's Euler. Get pi as pi. How do you get Euler number? Exponential. Okay, there you go. Exponential exponent. Exponent is, if we do this over this, get this one. Not a good result. But if we do this, what did we do? Exponential. If we did this or this, get 0. What am I doing? When I type in 20, seventy-seven point 45 000 minus this. There's the powerful temperature. Okay, first of all, we said this was 20, maybe. Yeah, that is the 20 degrees. That goes into this. 25 is the air temperature. We'll deduce 20 from this. These two will be done in the other. This 20 is always going to give us when we do the density of water power. Partial pressure water power. Oh, this is not P, this is rho. Of water. Water vapor, what am I saying? This doesn't have any bearing here then. Saturation pressure, which is this formula, which saturation pressure. This is that density that is actually this part, not relevant. So for 20 degrees or 25 degrees, you need to know this. Basically, you need to know this to plug in here so that it can do something. The goal is still to get this, get that. Are you telling me that maybe that's what I'm doing wrong? This T, if I recall from science class, this has to be in Kelvin. I cannot just plug 25 here. Makes sense. Which means this. Where is Google? Insert one left. We'll do Celsius. Kelvin boy. Kelvin boy is going to be what you see here plus 273. You'll have 25 degrees. We are getting somewhere. Awesome. So this was the right math. Yeah, it was actually over, was exponent over the temperature part. Okay, that's good. Which means this nonsense can be undo. Thank you. This P is essentially temperature, but you have to add 275. This, okay. This is also going to be 275. Right? 273. Coming all this way, getting stuck in writing the chain. Okay, cut this crap. This. No, it's still wrong. It's still wrong. Bail out. Bail out. Cut this. Okay, put that somewhere there. I don't care. This. Cut that. kind of need that. Okay, over. There you go. This. Finally. Something funny looking about. Power. To we did what which is the power. Yeah. Is P is such a weird number? Kinda there, kinda. So why is the Excel math checking? This is such a huge number. Ooh, 2735. There you go. There you go. This is the number. 2309. 2309. 20 degrees. 2309-ish. Round it up. Done. So now we have saturation pressure of water vapor. Well done. Now that value is this value going to be the pressure, which will come in from the game. I will just type it in as a constant. I'm not going to waste space in the constants. I may. We'll see. Now we are plugging in this number, humidity ratio of moist air. This is the 14.7 something, okay? This so that is actually coming out as this. So at some point I would like to get, where are we? Still Earth. When I put in 20 degrees there, I'm getting this. I'm going to write another equation so that kind of this, but this way, because I think the way it fits in here is expecting that value. I will later, of course, multiply everything, but it's going to be based on seconds, time. But here there's actually gram, kilogram. No, I don't want to mess up with that. So because it's going to arbitrarily multiply this by 1. And that is not good. So where are we here? So when is 20 degrees? Let's do a stupid thing here. When you do this, you get this. Not like this is e to the power of 20. Some other stuff is basically humidity ratio. Let's pick a new humidity ratio, H. H is such that E times this times p constant over the pressure minus p. This speed. So we have to be over, and you are complaining about the fact that you define b in more than one place. No, I didn't. By deleting some of the definitions of b. Did I do that in constants? In fact, I did. This b was the bullshit value. Water vapor saturation. Could we call it b? Vapor? V was the velocity. This is what exactly? Saturation pressure. PW. Pressure water vapor. Pressure of water. PW. RP. Where are you? PW. Ah, there you go. You're already giving me 0.04145. You're already giving me this. Is this what I want? 007. 0014. That's already what I want. I don't need to convert it to anything. Yeah, they did the gram over kilogram. We already got what we wanted. We are one step closer to. We still have the air temperature is 5. So actually, maybe I should make that other thing subtract 5. So this 20 is this is actually going to be minus 5 because P is the temperature, right? Means this now has to be 25. Everything is going to check out. Awesome. So now this is done. 50% humidity. I think I did some stuff there too. This is the difficult part. I don't know your science. So interpret this graphic. On the left side, we have Celsius, 0 degrees, 20 degrees, 25 degrees. The value we like to see is that 25%, 25 Celsius, 50% relative, 25. Somewhere here, we need to take into account humidity, and we are expecting to see a value like, imagine this is actually 100, 001. 001 is actually here. So let's go down this pathway, 25. So it here, somewhere here, need to see humidity. I think that is represented as this curved line, which is H 0% humidity. So I see when you get to 50%, follow this line and hits certain coordinate here, 25, 10. Fortunately, they don't have a table. I was going to, okay, I think they already say. 21 and then 50% is indicated as this. Fortunately, this is actually marked as 40 here. Ooh, I see. Because that wasn't exactly a percent. It's the kilojoule per kilogram. The enthalpy of the moist air is approximately. Nevertheless, we are still right about following this line. And then when you find this number, you go up here and then you actually. Difficult part is there is a chart which makes me think that maybe there was an equation at some point, or these guys realized that stuff fit a certain pattern and they made a chart. There's no equation and you just follow the chart to come to numbers. Doesn't make much sense to me, but where's the equation, man? The Mollier diagram is a variant of the psychrometric, chrometric. Diving deep. I think by now I know how to use it. How do you come up with this? So far, everything went well. But you need equations. Could turn this into a geometry problem, but this 45-degree angle. It's if I could find this 40 kilojoules per kilogram. Imagine it's here. So that draw a line for something like that. Really reaching here. Some point it has to cross a line like this. 21 between one like so when there's an intersection, then you still okay. These values are static. I know. This is where we might be stuck for good. Let me interpret this part a little bit freely. Can we bullshit our way, assuming that this is 0.01? If it's the same 40 here, 50% humidity, which corresponds to 40 kilojoules, so we are here, okay? So we'll be on this diagonal line. Good. Along this diagonal line, how badly these numbers change. Temperature drops or goes up. In other words, if we are at 21 degrees, the moisture is increasing. I bet this kilojoule is also increasing, which means this diagonal line is going a little bit slower. Like these values are increasing a little bit less drastically. But if the humidity is the same diagonal line, the temperature variation is when it's here, I'm gonna cross it here. Yeah, this is a big change. Like temperature drop changes this. However, it's safe to assume that the higher the temperature, the more moisture. Therefore, as this goes up, this goes up. Diagonal values, there's always going to be some kind of like this going up. They are still meeting each other around this value. You could actually bullshit. The only problem is you cannot really come to this value below 15% because you hit that kind of area there. Doesn't make much sense anymore. So I guess if it's below 15 degrees, could actually assume this is the new sort of until you hit zero, and anything below zero, you kind of use it. You could do the same thing for above 20 degrees or 25 degrees so that you go up to the next. So I don't know who is still online and watching, but let me know if bullshitting will work. I think this is where we might be stuck. I don't really know the equation form of this Mollier chart. Uh, Whoever this person was, respect. Very complicated thing to do. But I cannot work without equations at this point because that's not how computer science works. I remember What was this tool's name we are using? Desmos. Desmos if statement. There was something about writing conditional. Let's take this. Okay. Just want to. If you don't know it, I think I'm going to use the trick that I mentioned. Let's do an fx. This is where I'll actually bullshit. So if x is less than 0, here's where the bullshit is starting. If it's less than 0, then it's going to be this 0.005 in half. Not x cubed, 0, right? 3 zeros and 5 over 2. I want to write it as like that, as the multiples of this. It's easier to read. When it's between that and 15 degrees, did I say, okay, where was this? I had an easier time reading it here. When it's above 25, I said 15, okay? Between 15 and 10. How did I do this the first time? This, okay. This is a good one. So 15. Between 15 and it gets higher. Between 15 and 30, I'll assume it's 0, 0, 10. Between 30, it's this times 2. Sure. Then I guess between this, what does it do? The orange. The values are so small, it doesn't make much sense. I'll zoom in, or I'll multiply these values by. I'll do like g of x is 100 times f of x. Okay, even 1000. Don't render that. I think we are done. So if it's between 15 and 30, it's what? 10. Did that. 15 and 30. We are in this sort of box here. That's it. And sort of along this axis, we are actually assuming this. Anything below 15, we are entering this area. Well, I suppose I could actually be a bit more granular. Between 15 and 0, we are actually here. And we could actually do one more here. It's 30x is going to be this times. So let's call this Moliere point m of x. Okay. because good shit comes with names. Where are we? So this is essentially 0, 0, 1 for 25 degrees. 25 degrees, 0, 0, 1, which is 10. Multiplied by. Okay, we have this. Now we have this, this. Let's get this. And then maybe when we multiply this by, well, if you don't do this part, we'll actually get change the calculator type, that fancy number that we were typing in, 8 something, whatever, written, is 0.85. Something here has to result in, let's do that. What do we need? We need the theta. Something, pull this here. We need the theta. Where is the theta? Theta is this y. So I cannot type stuff anymore. Right? M of x will be okay, so calm down. T is there, plus. Not t, it's y. Brain spelled it. We multiplying, we are multiplying. That's a good thing. Yeah, we are multiplying a few things, then subtracting the a. A is and then there is actually this stuff, which is I think this is the minus part where we do the h part minus the 0, 0, 1. This. So let me recap. When this is 0, 0, 14 and when this is 0, 0, 1, which means difference is essentially 0, 0, 4/1000. That's what this is. Such a tiny number. Okay. But x is actually the temperature. P. This is actually m of p. P can actually temperature that is bound to A. G of p is actually this. What's wrong with you? Because p is already defined. P is defined. I get that. Okay, this is going to be a constant. Can I write this as m? It's a constant. And then I use this. So that is dependent on. And then this is actually g. No. We define h in more than. H is humidity. H is 0.75. This H was gonna go into this kind of calculation. It is no longer relevant. We'll bullshit it our way. H is not used. This H is actually here as a separate entity, so delete this constant. Come here, hit enter. It's been entered. Okay, we have something going on here. It's a good thing. Why can't I get this value like? Okay, what am I expecting here? Some number that is too little. We have 34.5 is y times s surface, which is 4 square meters. All good. Times difference of those two things, which is h minus m, is sort of a small number. So 4 times this times a very small number is going to give you 4 times 34.5 times 0004, going to give you half. Part that doesn't make sense to me is this. This is a constant. Why is this x and y? Should either go this way or this way. Yeah, how is this started as? Is this going to change when I change p? I actually make p like 10 degrees. Is it gonna give me 0005? Why are you fucked up? Why g? Oh fuck me. Is f? That fixes that. I'm cheating this. Let's make it step 1. Undefined. Fine, because this is less than 0, less than there you go. At least we know something's working. Okay. This 5 degrees is this. Should be a constant. Okay, let's not do f. We are, oh, there's the theta. Hello. So then y actually has to. Can we now use something like 2? There you go. Still wrong, but it's we have so far used t as axis. Normal is x. I'm not excluding the x, the possibility. The fact that this line is growing and it's not a constant line makes me think that something in this equation is depending on either x or t. S is a constant. You cannot graph theta as a function. Okay, so then that actually is error. Let's call this u or u. There you go. It's the constant. 0.6. That's more like that's what we want. Because now at least we can do 10. It's going to be something if we actually do this graphic. That's not like exactly what we are after. Is this value even correct? According to our calculations, not. Because I'll try to pull this here so that we can see. No, not like 30.45. So this way. 34.5. That's all good. Okay, let's plug in S as 1000. Pretend. We are checking the sanity of this. This H value is this value. 0.014. It's a little bit off. I typed this exactly from their page. This was a constant, which means PW is playing some role here. The fact that that might be wrong is, I'll say because I did it according to their math. So the fact that this is not exactly 10 is actually the point I get. So maybe we'll fudge it here. Do like this. So okay, when we do 20, are we getting 1450? Okay, it's that it's increasing, so we'll actually do this 200. 1455. Did they take this as like this? 63, getting there, like this. 5 something. Five, 9, 3, 5. Full 5. Done. As close as it can be. 146, 146. 595. Good. It's still 001, which is close enough. Now this number is not exactly, now of course they actually divided this by this, which then checks out. This is 47, so this is 7447. Close enough, okay? Because there's a lot of discrepancy. And 2% here will, which makes sense, 2% here. By hard code, there's, let's see, 0.009. Yeah, is the accuracy here is actually through. So for our intents and purposes, Chernobyl. This number will fluctuate, but it's okay. Maybe we'll take this into account as like, real enough. We'll see. We'll replace this with the in-game air pressure. This math checks out. We have the 0047, close enough. Okay. How did we get to this point? We said this is uh, per second the water operation. So if you want to go to the hourly evaporation, we shouldn't actually do this. 160. That is right. And if only I didn't actually lose the history from the previous unscientific calculator. Oh, it does remember. Awesome. Okay. This is what we found actually. By following their example, 0.047, said instead of per second, let's do hourly drop rate evaporation. We found 169. With our calculator, we are 9 liters off. So that's where we are. It's close enough. It's less than 10% off. Still a big margin, but it's good enough. So what value can I actually adjust here? This is actually 101,325. Where are we? So let's get this back to somewhat real values. Which is interesting because as the air pressure increases, evaporation goes down. Isn't it interesting? I think I remember reading about that. That was one of our exam questions in high school. Because when there is pressure and not enough airflow and all that jazz, stuff was less free to evaporate. So when the pressure goes down, say this goes down to 99, okay, 99, 165. So you gain like 5 more liters of evaporation for just 1,000 Pascal. This almost looks a bit linear at this point. It's like 5 liters. Of course, it's not as simple as that because everything also depends on temperature too. But I think this is exciting because let's try this. Can we actually plot this in? Let's do this q of y, actually q of x. Okay, let's give this. So this orange line is our evaporation ratio amount. per hour. That value will essentially be somewhere here, which kind of doesn't make much sense. Like, okay, we started this to find this point. The fact that we came to a number that we could justify. How did we find this point 85? Okay, that was many hours ago. Feels like a different universe. Here's what I'm going to do. Decrease the temperature. Naturally, the evaporation goes down. It went down to the point that it's not evaporating, it's sort of raining. Anyway, when the surface area is getting smaller and smaller, there's less evaporation. This is still drastically changing. When we say like 15, what actually is that? This is that. Therefore, H minus M is drastically high. Well, not so, because this also is coming. This is coming down. Let me double check this. This 12. Put you back in place. I think you were here. At 15, okay, 15 minus 10. 12, that checks out. There is some discrepancy, but I think it's close enough. Mind you, sometimes it actually throws things off really badly. When you get down to 5 degrees, will we read something along like 888? 10 degrees, like 5 there means actually this is 10. 870, did we get? 860, I'm impressed. So this is actually quite good. Not perfect. I wonder if I actually one digit wrong. Because we are trying to get this, right? Oh, I also changed this to 325. But that has nothing to do with it. 77345. Kelvin is 298. What the? Okay, 273, sorry. Here about 7235 over 273. This number is actually surprisingly close, but when it's 25, which means we could actually have 30 degrees here, right? Let's actually make this maximum to, I think I actually put a maximum here. Did I? Three one three zero. That's actually perfect. 3130 to 30 degrees. Well, this value gets put here. It's this 62198. Well, I guess the math really checks out, but the interpretation is a bit weird. Here's the reason why. When it's 30 degrees, our evaporation rate is 135 liters per hour. With what conditions? Get this up to 1000, or actually get this down to 4. Pick this number. For argument's sake, let's make it let's say we have 160, like a mini swimming pool for kids. Something like that. Takes quite a lot of water. So you have like 55 liters of. That still seems too hot. But I mean, this thing doesn't. It's the. Okay, 1000, right? We are only trying to satisfy this condition. It's 1000. We are trying to do this. For a swimming pool this big, when the water temperature is 20, so we deduce 20 centimeter water temperature from air temperature. So let's set the air temperature to 20. Here's the 25 air. So the water temperature goes into this calculation as P minus 5, which PW goes into some calculation here to give us the humidity thingy. And then we have this bullshitting factor here with the M. So the humidity plays a role here, which is basically this area here. XS minus X, which is basically the humidity ratio of saturated air minus humidity ratio air. Essentially, it's calculating how much pressure there is in the air and how much humidity can the air take, that kind of. So you multiply that with the surface and then theta, and theta is evaporation coefficient, which is also taking into account the wind speed, which is 0.5 meters per second, like this. So according to this, we should get a number like this per second. Of course, we don't care about seconds, we care about hour, the rate. We multiply that by 3600 which is essentially 169, which is kind of what we get. We know we have a few boo-boos here and there, especially this is not precise. But when this gets precise, it's actually close enough. Because I think when you do this, where you get value, same shit. Nope. Yes, it's one decimal more. Here you actually see 162.4. It's close enough because even this has some. We try to do this number a bit close to the reality, but we don't quite know what they used here. In the broken down versions of these numbers, they actually used any air pressure value, but they did not actually mention it here. For the calculation of this case, this air pressure that they use, I think is closer to this, which actually pushes this number to a higher value, 167, which is even better to this, like even closer to this value. But we'll actually take the standard air pressure, which is this, I believe. So we are in a good spot. Let's replace this with M. So this result means when there is half a meter per second wind speed over a swimming pool that is 50 by 20 meters. On a day when air temperature is 25 degrees, under normal sunny conditions, meaning there is no air pressure change, this swimming pool will lose 155 liters of water. That's a lot of water. A lot of water. Seriously. Yeah. So for our compost, we have only 4 square meters. It's just a tiny, 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 tiny. This is the number that we were see, 0.62. That is basically this. But in the other number punching situation, we came up with this 0.85, but now this 0.85 can be this. So Q and X. So instead of mapping this, we now do this as Q, and now we can actually do here. And let's actually pay attention to the graphic. So these values will now change, but at least they will be much more accurate. So now this equation takes into account, these two will still actually have to pick which one we are using. My heart is still set on the K function. But this equation now takes into account passage of time, temperature, surface area, and if it's raining or not. Now, this number that we found, every hour, our compost unit is losing roughly 620 milliliters of moisture. When it's raining and it's adding zero point 0.5, it's compensated. Now let's stop the rain. What happens? I'm going to take some water, come back, and then maybe interpret this a bit more and sign off. Let's see. It was such a journey. Time to make the final comments and sign off soon. So that 150 is still sitting there. I'm gonna try a little bit of, let's say, this one. This, that's, which is essentially the same thing. These two are now. I think I'll just change this back to. I think we did everything right. But I think it's time to conclude. Just to recap, we now have a minimum and maximum or low and high threshold. Could be the minimum or maximum, to be honest. We are doing, assuming this is the water. This display is also here too. We didn't actually replicate it. You want to be in the safe green zone, okay? So when you have some material, GNB, such that it's like 40 liters of green, 60 liters of brown, so that you need some amount of water. You are not adding more water, then the water will evaporate. We have written that function, actually two functions, but the evaporation rate is going to depend on the surface area as well as the temperature. Which means the higher the temperature is in the game, or in this case, the overall air temperature will but this is actually the compost temperature, which will kind of make sense. The air temperature will actually impact this compost temperature, which will then impact the evaporation rate, so we've done that part. Oxygenation has nothing to do with the water evaporation. That's so wind speed might play a factor. Actually, we will also have that too here in the weather. We'll have wind speed, so we'll see how it goes. And everything taken into account, whether it's raining or not, we are actually seeing the drop rate. If the player doesn't add any water, at some point around 72 hours mark, we are actually entering this 125 sort of danger area. In this case, it's 29 hours, and in this case, the other case, I think 41. Yeah, it's 72 hours, but that was the earlier version. This is it's somewhat more realistic, but still, we could actually fudge the numbers here. But at least we have a more realistic drop rate. I think our goal will be these values are still dropping too drastically. The curve is right, it's just the slope has to be flat. But that's all for today, and we'll most likely catch up tomorrow, continue this work. So